Alright, so last time we started our stack language, which is a stack-based language, and yeah, we just start to tokenize some numbers and some, I guess, end of file and illegal tokens. And today I wanted to try to go into the assembly, so we'll have like a short intermission just to see how the assembly should look like for this really small example. So I'm also working at the same time with some ideas on how to have, like, for example, data structures, maybe functions in the language. And it's gonna be a bit different than how we are working right now. So probably it's gonna be a bit of a difference, but I still think it's a good idea to try and build this assembly example first, just to see how we'll use this tag language, because I'm curious. We'll have like maybe a memory allocated for the stack, and then how are the instructions gonna look like. So I think it's still a good idea to take this example with numbers and operators, implement that as a first step, and then go into, okay, let's add data structures. And I think that's how I want them to look like. Like, you have the keyword data, then you have the name, and then the fields in maybe parentheses or something like this, with the types and names. And then functions would be something like func, and then the name of the function, then maybe the type of the function. If I figure out how we can have some type checking, that's gonna be really useful. But right now I'm not sure how we are gonna do type checking, because it feels like you have a stack or like a list of random objects in that list, and how are we gonna keep track of what type each object has? Right, it's gonna be interesting to figure that problem out. But yeah, for today, my plan is to implement in assembly how I think a program is gonna be compiled into, and then we are gonna try to take our current code made in C, the compiler, and try to make it output that assembly, I would say. And the assembly language that I'm gonna use is gonna be Phasm, because I used Phasm before and I think it's pretty nice. I mean, I'm still just gonna use the basic operator. I'm not gonna use variables and ifs and stuff like that. I don't even know how to use them, but I know it's possible to have more complex stuff in Phasm. But I mean, I'm just using it because I don't know. I don't want to use Nazem. And okay, so let me just develop to download Phasm. And I think another really good resource, maybe to understand this entire flow of having the compiler, splitting everything into tokens and building an AST and the assembly, is in this compiler tutorial project, which also have a video, like it's the entire thing in one video of like 4 hours, like the compiler from scratch. I can link everything in the description, don't worry. And yeah, like this entire thing, it's like 700 lines of code, and we have like a really simple language, right, that we can use. And I think it could be really useful to, look into this code while we try to implement stuff. I think it's pretty good resource to copy from, in a way. So yeah, probably we'll take some we'll look a bit into that. Right, like this language is extremely simple. It only has a few instructions, and yeah, it doesn't even have functions or anything. It's just instructions, go to labels, and input and output, I think. Not even sure though if we have input, but anyway, and it only has integers. So it's kind of similar to what we have, right? So yeah, like the plan would be to just have something like this, an assembly file where we, let's say, not even sure, maybe just do something like, first let's try to get, oh, where's the readme? First let's try to get a 0 on the stack and make it as the return code, and then we'll do addition of 2 items, right? And that way we kind of figure out how the assembly should look like for this thing. And yeah, so let's have something like main dot what's the extension? Asm. Let's have main dot asm. Right. So in this one, I mean, here I had some comments. This is the cool compiler assembly, so it's a bit different than this one. But see, here I actually wrote some assembly, right? But in this project I haven't. I just put everything into main.c. So here you can see I created this executable. Oh, and yeah, that's also the other difference, right? Because here in this compiler tutorial, I linked everything as an executable. Probably doesn't make sense right now, but here I linked it as a, not as an executable, but we use ld at the end to link it. So that could be a, you know, something to keep in mind, because if we try to do, let's say in the future maybe we want to do FFI with C, right? But I'm gonna try to do it in, you know, a bit of a better way, where instead of you having to implement all the libs like this, by writing the assembly code for it and everything, I think I want to do it, I don't know, somehow being able to do it from the code somehow, right? Not sure yet how that's gonna be possible, but I'm gonna try to do that. So yeah, so the useful thing I think is gonna be in the allocator, the first step, right? So we'll need some kind of section. Oh, and maybe we could even just go to the cool compiler, and I'm pretty sure we built something. So if we look at build, oh, we have some assembly. Let's see the hello assembly. Right. Yeah, so see here I have this format ELF64. Don't really remember how I did that, I'll be honest. But I would say, so if we check, yeah. Anyway, so let's try to do that, right? So first maybe we do the same thing as here with format ELF64. And then we are gonna need, so this is some functions, we don't really care about them. The first important part is actually the start. Where is it? Start. Yeah, sure, here we have some, you know, constants that we use in the other language, but we don't need them. And this part is the let's say entry point. So I would take this one, just put it here, so it's section executable. We have start, and we could have a function allocator in it which initializes the, like the stack, let's say, let's call it the the stack thingy, right? We want to have like a big stack for our stuff, but obviously we also need to allocate. Yeah, that's for the future. Right now we just have a big stack, and we put numbers on that stack, so that's the only thing. And then in here it's gonna be our main stuff, right? We can just put it here and then exit program. I think this is the syscall for exit, and this is the first argument, right? We also have to remember how the arguments are passed in assembly, right? But that's the main stuff, right? And the allocator, we can start with some data writable, but we don't even need. Actually, let's just say, so let's just put this at the beginning, and this is gonna be the memory layout as it says here, right? So we could say that it's gonna be called heap. Doesn't really matter. Let's say stack position and stack end, right? I think I want this stack to be like a constant size for the beginning, like only have, let's say, 64k on that stack once, and that's it, right? So for this we use the break syscall, right? And here the increment is set to 0. So when the increment is 0, we just get back the current position, right? Something like that. So this part, let's just say that instead of calling this, we initialize the stack like this. So here we do the break syscall, and when we use an increment of 0, I think we have the man break or brk. Well, that's weird. Like there should be this thing, and here it should say that if the argument is 0 or something like that. Okay, yeah, calling sbreak with 0, we find the current position of the memory, right? So the beginning. So that's why heap position and heap end are gonna be that, like 0. And then we can use sbreak with a number. So for example here, 64k to okay, so let's see. We do break, we put I'd say if we call it with 64k, no, and also another project that I'd say could be useful. It's also another compiler, but this one is for BF compiler. You know what I mean? Here it's also just written in C, everything. So just wanted to see like allocating the main part, because brainfuck has this, see, like it calls the break syscall with 0 to get the beginning, and then it adds, oh yeah, it makes sense why we added. Okay, so if we go here and we do something like this, right? So here we initialize the stack, let's say. So stack position and stack end. Save the end of the stack, and here we add 64k, and we also new end of the stack. We don't really need the end of the stack in this example, but let's say we still keep it, right? And stack position is gonna be the position of the first empty element from the stack. Yeah, and I mean, if you go out of bounds, it's your problem right now. In the future, maybe we'll have like static checks that you don't go out of bounds, but right now it's like, it is what it is. So by doing this stuff right here, we initialize a really big array of 64k bytes, and we are gonna have in a stack position the beginning, like the first element, and stack end is gonna be, let's say, the next element after the last one, right? So it's gonna be stack position plus 64k, as you can see here. So putting a 0, like doing the, let's look at the readme. So if we do this 0 here, it means that we push a 0 on the stack. So what does that do? Well, you'd say, oh, you just use the push keyword, but I mean, that uses the actual stack. We want to use this place in memory that we just allocated. And obviously we could have just created an array, but I feel like actually allocating memory with break, it's gonna be more useful to understand, you know, what's gonna happen in the future with all of those like objects. So what do we want to do when we push? So let's do like a comment. This is the, let's call it a subroutine or something, like a function for pushing a number on the stack, or maybe procedure. It's like an algorithm, right? So what is going to happen? Let's imagine that we have one register, although if it's going to be like a function, I don't really want to have it as a function though. I don't know if I want a function right now. Although it could be cool to have a function, don't you think? So let's have some constants, right? And I'm gonna do something like this, arguments. So argument 0, 1, 2, 3, 4, and so on. Right. Okay, so I'm probably gonna just copy this thing, the copy method, but I'm gonna call it push method or push algorithm. Here, I don't think that input is gonna be anything interesting. We'll have, I'm curious, do we have maybe inside of something else, like for example random. Let's see. Huh. That was a bad example. Okay, Raylib, I'm pretty sure Raylib has a lot of, oh yeah, here I said that stack contains stuff. Okay, I'm tripping. So prelude, right? The stack should contain the things. So I don't, that's what I say, that since this is not gonna be OP or anything, how can we, let's say int.push or something. I think you can have dots in the names. Okay, so the push algorithm, Rx is gonna contain probably nothing, and the stack is gonna have the thing that we want to push, right? So on the stack we can use this example, like x object. Damn it. X is gonna be an int, right? Usually I know that you want to save RBP, set up stack frame and this stuff like this. Then we allocate the variables, but we don't have any use for variables. Then we want to save the RBX register. That's usually the like if you search for assembly like conventions or maybe I don't know, like call conventions, sure, it's like for something else, but I'm pretty sure I remember that it says that functions don't change RBX, or there are a few registers that are not going to be changed when you call functions. So let's try to follow those rules, right? For example, RBX shouldn't change after a function call. I think RAX is going to have the result, so that's surely going to change. Okay, then RDI is the first argument in some cases, so that's pretty much gonna change, and yeah, it makes sense. And then the end. Yeah, I just want to kind of use this, stuff to remember how to use assembly, because it's been quite a long time. So here we restore the RBX register. So basically it hasn't changed, right, in this function. We deallocate variables if we had any. We restore the return address and return. Okay, and here we do our actual code. So I said that on the stack we have the object, right? Let's see an example where we have something on the stack. I think equals has something on the stack. So here we did something weird, and then we can move, let's say, into RDI, and RDI and RSI are gonna be like random things. So like random variables that we can use, random registers. So here we take, or I guess we push arg0 basically. I guess that's what I want to do in this place. So we want to push arg0 on our stack here. So we put it into RDI just to have some something going, and then we want to do something like this. We want to move somewhere into memory, and that place should be stack position. So we take stack position, and here are the, so if we move a stack position, okay, so right, maybe let's see the yeah, it's like interesting how, because here I actually managed to hide everything behind this allocate call, and you know, that's really cool that I managed to do something like that. So here allocate, I think you put how much size you want, right? So at some point we actually need to increase the heap position, but I'm not sure where that happens. Because that has to happen somewhere. It's interesting. Oh, here the Jesus Christ. I mean, it's yeah, really complicated, but you know, we'll figure it out. So because the idea here, if you can see, it's like object copy. So this thing was actually allocating some memory, right? So we were taking the size of the current object, we were allocating that size, and then we were copying the object at that memory address. But the question is, because that's what we are kind of doing here, we take this is the object that we want to copy, right? It comes in the RDI register. We actually write it to stack position because, as I said, we know that we only have 64k bytes. We won't do any allocations. We just copy it at the first empty position, which is stack position. And I think that now I want to increase the heap position, but I don't remember how I did it here, and that's what I'm curious about. It's like, how did I manage to do that? Because that's pretty cool. I don't see it being changed. That's what I'm worried about. No clue, honestly. Like here, what does this do? So T0 is the, let's imagine that heap position is the first empty place, right? So T0, we put a variable, we keep the current heap position. Then here we calculate where this object is going to end because RDI holds the size, right? So we see, okay, T1 is gonna be current position plus how big the object is, right? Then we check if the current ending of the object is smaller than the current heap end, because if it's bigger, then we have to allocate more memory, right? And after that, we were just writing heap position is equal to T1. So, I mean, oh, yeah, that's actually what we are Yeah, I was looking for this exact thing, but I don't know how I didn't figure it out. Um so yeah, actually this is kind of wrong. Because okay, let's think about it, right? So if we take this exact thing, this exact value, it's gonna be someplace in memory, right? If we dereference it once, it's gonna represent the place in memory where we store the variable, and we have to reference it again, or like dereference it again to be able to write into that buffer. So this thing wouldn't work. So what we have to do actually is, let's use RSI for this thing. We have to take a keyword from stack position. Maybe let's do something like this. Let's put some comments. RDI is arg0, right? RDI is the first argument. Then here RSI is gonna be, let's say it's a pointer to the stack, right? So imagine that if we do something like this, if we do something like this, it's a double pointer, right? If we dereference it once, it becomes a pointer. Then we want this thing, and I mean, I don't know how to, maybe like it's a reference to the stack or something, right? And here stack like 0 becomes RDI, right? That's the idea. Not really sure how to write this to make it more obvious what happens, but yeah, here we have to dereference it once and then once again. That kind of sucks, like being able to explain this stuff. But anyway, and then what we need to do is something like here. We need to add, I guess we can just add 8, because that's the size of, so to stack position we add 8. So we just do something like stack plus 1 position. Right, we go to the next position. Yeah, the comments are not the best. I don't know if you have to add 8 or 1 though. I'm pretty sure here I have some don't have. But maybe I could have something like some constant for the size. Maybe something like stack size is equal to 8, and then we can have here stack size. Yeah. Right, so maybe if we go again through this logic, here we kind of do something like take the first argument, that's pretty simple. Here we dereference the stack position, which is a double quad word. So if you think about it, this thing is gonna be just a number, but I guess it's important what that number represents, and that number is the current position of the heap, right, for the program. So RSI is going to contain that current position. Okay. And here we write to that current position. Maybe that's, better to think about it, but yeah, whatever. And RAX doesn't really need to point to anything. Or does it? For now, I don't think so. Okay. So I'd say then oh, and yeah, that's also gonna be interesting. When we call functions, pretty sure we call some stuff around here. So for example, memcopy, but for internal functions, I didn't really. Let's see, maybe I called some more interesting functions. Just curious about functions with some arguments. Huh. Because, like the easiest way to figure that out would be just to see the code, but maybe like, oh my god. Oh yeah, it's called dispatch call. What? Oh, that's just the print. Oh, this was the new type. Oh, maybe this one. Right, so, oh, actually, that's interesting. I was just pushing the arguments. Is that right? I think that's what I'm doing, yeah. Push something. Oh wait, I could just check the like pretty sure we are gonna have some push and then call if I wait, it should be in main dot main here. Huh. Yeah, see here we call something. So this would be like the function call. This is the first object, and here we load t0 and push it on the stack. So yeah, we actually use push. And the other important part which I remember Oh yeah, here is the comment with what happens is that you actually need an even number of pushes for some reason. Which is like, what the fuck? Like, that's so weird, but yeah, that was something that we learned the hard way, but let's see if it works without it. So yeah, like probably the easiest way to do this stuff is just push let's just do push 0 int dot push, well, call int dot push, right? And at the end that should be on the stack, right? And I think exit program is probably going to be something like another small function. So let's just copy this thing. So like it's going to be exit algorithm. The exit algorithm, I want it to return. So on the stack or like that doesn't have anything, but the return or like output, as I said here, for output, RAX should be the RAX contains the code. Let's say RAX should contain the code. So we do the exact same thing. Then we need to take the stack position. That's the first thing. Stack position. Oh, but here I made a mistake. Here it's add. We take the stack position. And here it's also RSI. No, it's fine. That was fine. We take the stack position. Right. And we want to move into RAX. We want to move into RAX, which is the output. The previous, so keyword. Can I say minus stack size? Can I say that? So yeah, we take the stack position, which is the start, like the first empty slot in our stack. But you know, like how does the stack works? Last in, first out, right? So it makes sense that we take the last element. It's not a queue-based, like imagine a queue-based language. That's gonna be interesting to think. But yeah. So, well, actually, this is a pop, if I think about it. Pop algorithm. Because, I mean, it's a peak. But I think I want to do a pop as well. So, yeah, what happens here? It's, let's say it's gonna be pop. Although pop is not really used, if you think about it, but yeah, let's call it peak because pop doesn't really exist in this language. So int peak is gonna give us in RAX the the last value from the stack, right? And that's going to be used here. So we do call int peak, then we move RDI RX, and that's how we try to exit the program, just to be aligned with everything. On the main method. Okay, so if I do xdevelop, if we try to FASM main.asm, oh, wait, I don't know how it's gonna be called. Main.o. Let's maybe call it something else. Let's call it test, because I'm not sure. FASM test asm. I'm not really sure it's gonna create test.o, right? And as I said, we need to link it. Okay, so you can see that echo status, it's 0. And if we go here and make it 1, let's FASM and ld test.o. Let's maybe rename it to test. And then we run test. We actually get a status code of 1. And if we, I don't know, do 69, we get 69 as a status code. So this thing kind of works. I know it's a bit over-engineered, and we could over-engineer it even more, like at this stage. But that's how I would imagine the assembly to look like after we after we generate it. So let's see what else can we over engineer here to make it easier, because now I think I want to do the addition. So imagine that this is like we take this SL file and it converts it into this thing. That's how I would think about it. Right. I mean, to be honest, we could just take this and put it here and say, oh, that's actually how it's gonna be implemented. Because maybe push doesn't really make sense to be a function. But who knows? Huh. Yeah, I'm not sure. I'm just thinking that maybe we want to have something like it's a good idea to have it as a function, because in the future, let's say we want the stack to grow in case we reach the limit. And if we have it as a function, we can always just change here the logic, and we don't have to change here anything. So yeah, but I'm pretty sure what it's actually gonna happen is gonna be something like move RAX 69, and then we'll have something like this. So when we have the token, we just put it into RAX, and then this, well, I actually forgot. Actually, I forgot about, so here we push the instruction, right? But then at the end we have to read the argument. we actually have to free it, right? Because we pushed something and then we have to free it. And I remember that for working with floating numbers, you actually have to have an even stack, so even number of arguments, or in other words, it's 16 byte aligned or something like that. Otherwise, floats don't work. So probably this will still work, right? But the idea is we have a token 69, we push it on the stack, this part is a bit annoying, but I mean, at the same time, we could just say that, okay, we don't use the stack, we just do like input RDI is the integer. Whoa, what did I do? So we don't even need to push anything on the stack, we just say move RDI RX, and that's how we call to these functions. So here it's actually move RDI RDI. Okay, so it's not even needed. Right, so that's maybe how we are gonna do the call to push. You put something here, you call to push, and as the input RDI is an int. Right. Now let's see what happens if we push another thing. So let's say this is 42 and this is 27. What would happen if we push two things on the stack? Okay. So now let's imagine, I mean, I know it's not, it shouldn't work because we have two things on the stack. All right, and as I said, we should have some static checks that we cannot do this, but for now, obviously it works because we are just working with assembly. So that would be that. But what if we try to do a plus here, right? What should the assembly look like? So I'd say that yeah, if I'm being honest, like this doesn't even need to be a function, but and like maybe this is gonna be more efficient. Obviously without the call to int push would be even more efficient, but I'm still thinking about that that part. Like of course this should work, right? Without the call to functions. But my question is, so stack position, because I'm pretty sure I mean, we can do multiple things. We can say that the stack size is limited and you cannot change it, but that kind of sucks. At the same time, no, yeah, it would make sense to have it limited. Like even the stack size of, yeah, let's say that the stack size it's always gonna be limited. I don't really see why, like how you would benefit from it, because it's not like you're gonna add 1 million things on the, like how are you gonna do that actually? Yeah, that's a good point. So yeah, that's a bit of a bummer that we wasted some time on coming up with the functions, but I think, you know, it's still useful just to remember how to use them. But maybe the actual code should be something like this. So here it's like doing the same thing but without the function call, right? And how would plus work? So here we can say push 42, push 27, and apply plus. Let's see. So if we apply plus, I would like to get from the stack the first thing, right? So we get, let's say, so it's fine that we can use multiple registers. So maybe we can have a convention that RAX is going to always be the stack pointer now, because RX could be the, maybe RSI is going to be the stack pointer because it has an S in it and it sounds interesting. Right. So like that, here we take into RSI then the stack position, then into RDI we put the current word, then we subtract this thing from the stack position, so we took into RDI the first argument, then we put into RSI again the stack position, which changed, and into RDI we cannot really move again this thing because it already has a value. Oh, here it's RSI. Right. But I guess we could try to add it. Or maybe move into RAX and then add RAX RDI. But I'm pretty sure we can just do add RDI like this, and it's gonna, RDI is gonna contain the addition. So let's go from the beginning, right? RDI has 42. We take the stack pointer, we save 42 on the stack, on the first empty position, and we advance the stack. Do the same for 27, right? And here when we do plus, we put into RSI the current stack pointer. First number from the stack, move the pointer backwards. Do the same thing. Add RDI, move the stack backwards one more time. Then we actually need to take the stack pointer again. We need to push this thing and then we need to add it. So this would be something like pop, this will pop 27, this will add 42, it's like also adding it, and here it's push 69, right? That's what happens if you think about it. Sure, here just for the memes we could also say this, and basically this is pop is gonna pop 69, right? Like that's what basically happens. So yeah, I think these are gonna be the building blocks of our language. Right, these pieces of code. This is the template to push something. This is the template to pop something. Sure, adding stuff. But I feel like in the final language it's gonna be a bit different. How adding stuff is gonna work. Okay, let's say that this feels kind of fair for now. Maybe we should try to actually implement this thing. I mean, shouldn't really be, I mean, we only have numbers right now, but let's say we add plus, because plus wouldn't be too difficult, right? Just to have a plus. Stack token plus. So yeah, let's add plus to our tokens. All right, and here stack token to string. Okay, whatever, it's just gonna do that. Okay, so stack lexer next. Yeah, I just realized, if you remember from yesterday, I said that yeah, but I feel like this is gonna be too long. So if we do, for example, let's have else if. Here's gonna be the condition. Lexer ch is equal to plus. So if we have a plus, I should do something like this, which I don't really like. But if I say here it's 0 because I'm too lazy to write it, we'll have a segmentation fault. Anyway, here should be plus. Yeah, like here, for example, we cannot I mean, I could have a default slice. Yeah, I don't know. It actually kind of sucks that you can say that, but anyway, so let's actually have the slice here, because I'm pretty sure some of these are gonna use a string slice of 1, and then we can put here slice, and here we can also put slice. Right, but this one has a slice of 0, so that's also oh, and here we just do that. Okay, so maybe we can do something like a do while loop. Do while token.kind is not stack token end of file. Yeah, so kind of works. Again, I don't really like this printing though. Because it forces this stuff. So it's like these things don't really need to have a slice, because this is a plus. We know the character is a plus. We don't need to see it as a plus. So it's kind of useless. So if we go here, maybe we could do something like, so we don't really need this part. If token dot value is equal to 0, we do something, and else we do all of this part. But yeah, here it's like, oh, you cannot say that, so maybe .str is equal to null. So if we don't have an str, then we do something else. Let's see how we can maybe make it a bit shorter. So pretty sure that's gonna be at the beginning. Pretty sure that's also gonna happen. String builder append. I'd say this should be the first thing, and we'll have only that. So fail to format token. And that's gonna be the beginning. Adding the token kind. Right. And if it's not null, then we want to own the buffer. We want to append this thing to our SB, we want to free the buffer and set it to null because we just use it here. But see here, we could maybe have another char pointer buffer because it's another it refers to another buffer. So yeah, maybe this one is better. Because if it's empty, then it's not gonna add this extra garbanzo, so yeah, it looks a bit better. Okay, anyways, let's do the important stuff. So let's take a look again at the assembly. We are gonna have so I think stack SZ is important. Okay, so all of this is always the same, doesn't change in our case. So let's have maybe something like, you know what, I'm just gonna do it using fprintf. How can we do that though? So let me see, fprintf writes to something. So I could say file pointer output is equal to std out, and then output. Okay, let's try to make a macro. qa shift I tab f printf output comma okay, so looking interesting. Oh shit, I forgot. Okay, let's go back. Let's go back. I can change it though, so let me just, we can print this one, right? And let's but I don't know the character code for enter. Yuck. Okay, anyway, let's do again. Let's do another one because it's pretty easy. F qa shift I tab f printf output. We do that. We do, oh, I'm stupid. It was like this. Okay, didn't even have to, like, it was like backslash n. I don't know why I tripped there. Oh, I didn't expect that. That's funny. So here it should have kept the tab somehow like that. Yeah, whatever. Still looks decent. yeah, so probably this is how we are gonna do. Okay, so let's recompile it. Right, it places the code, right? That's cool. Now if we go here, we can see that we have some pushes and applies, and then at the end we have this exit program, right? So this thing I think is gonna be like exit program. Maybe even like this, I don't know, exit program. So exit program should come at the end. I know, I'm not sure how I would have made. But yeah, if you remember from Cool Compiler, I actually implemented like a really complicated format printer for this stuff. So yeah, maybe we can do it again. Anyway, so we have push and pop, I guess apply. So let's implement push first, right? So instead of stack token to string, let's do stack token to assembly. Stack token to assembly. Why not? Stack token to Asm. So still gonna use string builder, obviously. And now it's gonna be based on the kind. So let me just take this. So we need token.kind. If we have a plus, it's gonna do something. If we have a number, we are gonna do the push, right? So let's try to string builder. I mean, there are two options. I either pass here the file pointer and write straight into it, or I generate the assembly. Okay, here I was directly printing. Okay, let's do direct print. So file pointer output. So we don't use a string builder. Okay, so if we have a number, so this is gonna be a void. If we have a number, maybe it should be like an integer, so we can return 0 or something, like it was fine. If we have a number, we need to push it. So let's put our, let's do it like this. Right, but here it's going to be like a string, and we put token dot, I cannot say token value, so actually we kind of need this buffer, but only here. Oh, okay, fair enough. I mean, why not? I can use parentheses, like brackets. So here we have the buffer, then we need to maybe string builder is, no, string slice to own, that's what I'm trying to use. The fuck? String slice to owned. If it fails, it fails. I wouldn't necessarily just panic, but maybe return. Let's use the defer. Maybe it's better. I don't know. Could even have something like this, and then here if buffer is not null, then we ds-free it. Right, and here we put buffer. So yeah, this part is pushing a number onto the stack, right? And the file, oh, and then we return defer 0. And see here it's gonna also free the buffer if it was created. That's nice. Here for plus is gonna happen quite a lot of things. For end of file, I'm gonna say just return defer. Maybe here we return defer with an error. Like something, for example, log error, illegal token. Or maybe it's gonna be easier to just call to this thing, stack token to string. Let's do something like this, stack token to string token. Right, kind of makes sense. And here is gonna be return defer 0 for now. Let's add something like this. Let's put a to do comment. And now here, instead of this stuff, I can say, whoa, I forgot already. Stack token to assembly. Stack token to assembly. Output and token. Right. So now if we compile this thing, we should see the pushes, right? Pushing 42 and pushing 27. And then exit. So if I write this thing into example.asm, and let's say we say example and echo status, we have 27 because that's the last thing that we pushed. But let's try to do addition now. So we should go here, and inside of test.asm we have how we do addition. We do a pop, then we do an add, and then we do a push. So let's copy all of this, because I'm pretty sure it's just gonna be this. All right. Because yeah, I think that's gonna be it. So if we recompile main and then we generate the assembly, no, let's have that, and then let's actually call it example and run example, and then echo status, maybe even wait, what? Yeah, makes sense. Echo status 69. And now if we go into example.sl, what if we do, I don't know, push 6 and then a plus? Is it gonna be 75? It actually is. So we can even have more complicated, like let's say, operations now. Shit, I don't know if minus is gonna work. Oh, it actually works. The only issue I have with minus that I just realized is, well, it's not an issue though. It's just that here we need to make sure that minus it's either from the number or from the operator. And I think what I'm gonna do, it's steal something from cool and say that this is gonna be the symbol for negative numbers. Or is it too lame? I don't know. But it's like, well, you can just do it. Well, another thing that we can do is maybe even have something like define plus symbol. Right? And then here, the plus symbol. But minus, you know what? Like, I think minus is gonna be quite, it's gonna be a good example of like implementing this thing. So maybe it's worth keeping it like this, because you'll see how you actually need to pick in advance to check if it's just a minus or not. So I think that's gonna be useful, because we have quite a lot of symbols in my plan that start with the dash. So yeah. But again, I feel like maybe we could make it easier. But yeah, it kind of depends. And here, let's just rename this to symbol plus. Let's have it starting with something. Symbol plus. Yeah, I don't know if I want like a special character here. Oh, and you know why would be kind of bad to not start with a minus? It's having to actually interpret. Like usually in cool, the tilde was an operator, wasn't really part of the number. So yeah. Anyway, let's add minus. So let's do here symbol minus, just to show you what it's gonna happen. So we have this thing, symbol minus, right? And now if we have a minus, it's gonna go here. But what if straight after the minus we had a number? It should have come here, right? So how are we gonna fix this? It kind of sucks that we have to duplicate, but yeah, like not that big of a deal though. Like what I would do here, I was just thinking that maybe we could. So I would just check that it's a minus, and then let's check that the next character is not a digit. So how can we do that? Is by using lexer pick. So here I can do something like stack lexer pick and then pass in the lexer. But let's do it's a minus and not is digit what we picked, right? So if we have a minus and the next character is not a digit, then we are sure that it's gonna be a token minus. And in case it's a digit or a minus, then yeah, it's a symbol minus. And let's put here symbol minus. I could even have that symbol minus. Okay, but now we don't have the token, which is fine. We can just add it really easy. Just looking around, I don't think we have anything else. Okay, so stack token minus. Okay, and here it's gonna be exactly the same thing for minus, but here instead of where is it's here, right? Here we need to sub. Oh, and yeah, that's gonna be interesting. Is it so clang? Let's see if it still works. So it should be 69, yeah. But what if we do a minus here? Is it gonna be the right value? And it's not. And I wonder why. I think I put the variables in the wrong order. Yeah, so wait, does it make sense though? Yeah, I guess order of operations is gonna be an interesting subject here. Like if you apply minus, which thing is first? We should check the reverse Polish notation and shit like that, but if you think about it, we push first 27 on the stack, so 27 is on the stack, then 42 is on top. If we apply minus, I would say that the operation should be 42 minus 27, so like this. Right, I would say it's gonna be like this. And this one should be the negative version. But, you know, since the status code, I think it's like only a char. And it's also unsigned, so it gives you 241, which is minus 15. So should still work. Like if we do 15 plus, it should say 0, let's say. Yeah. So I think, yeah, like minus is gonna be a bit tricky in this language because this is the first operand and this is the second one, I would say. That's how I would think about it. Right, like if you think about it, on the stack 27 is the first one, so if you do minus, I think it should be the first one minus the second one, but yeah, we'll have to see if this is actually the case. So yeah, that's kind of the idea of like a stack-based language, but it's extremely simple right now, right? And how we do the assembly for it, I feel like, yeah, some of these things are like a decent start. For example, the stack, I think I'm gonna keep it like this, having a size of 64K limited. You cannot have a bigger stack. And then the next step would be to actually have, so like we did all of this today, like just a quick hack just to get used to the assembly and everything. But I think I want to spend a bit more time thinking about the language spec, obviously, and actually start with like data structures, functions. And I think that's how this thing is gonna work. I'm not gonna put on the stack each field. I think how this thing should work, but I'm not sure yet. But I think how this thing should work is we save on the stack the address, or like you can imagine that on the stack we have, it's an IVEC2 and the address is here, right? So then you go to that address, you take the object, and that object itself has these fields. So on the stack you have only one integer that represents the memory address of this object. We don't really store the fields there. That's how I think it should work. Like we allocate the memory on the heap, and then we use the stack as basically as local variables. So it's, imagine you have a programming language that makes local variables more difficult to use. Like, yeah, but it should be cool to solve problems. Like, for example, I was tinkering around with how are we gonna solve, for example, dot product for IVEC, and it looks like quite fun to try and figure out how to use only a stack for doing dot product, for example, right? You have to do DAP and then take X, swap, and all of this bullshit. But yeah, it feels quite rewarding to figure out how to implement functions in a stack base. So yeah, it's more like, let's implement it so we can play around and do puzzles with this programming language. I think that's funny. Right, so that's how I think data structures should be. Like, you just store the pointer on the stack, and then you have a place in memory where the actual structure is. And then probably the compiler, I think, should create util functions. For example, the constructor for an IVEC, you put 1 and 2 on the stack, and then if you call IVEC2, it actually creates that memory, right? And on the stack, it replaces 2 integers with the address to the IVEC. Alright, so that's how the constructor should work. And then I think, because I was playing around, okay, what if you just do this? Because it looks really cool. But wouldn't it be more awesome if you can put the name of the fields and then the compiler would create these getters for x and for y? So if you call ivec2.x, it actually takes an ivec2 reference from the stack and it gives you it places on the stack, it places the int. That sounds interesting to me. Like, could be useful, like the compiler creating this function that you can then use, right? Like here. Right, and then, you know, you can write your own functions like ivec dot. So that's, yeah, I don't know. And I mean, probably if if you watch this far, you probably are familiar with the idea of dupe, swap, rotate for stack-based languages. So like this could be, for example, not necessarily keywords, but again, functions that are implemented by the compiler itself. So you can duplicate the first item, you can swap the first two, rotate the first 3 items, and so on. So yeah, and for now I think that these data structures, being able to create your own data structures and these functions maybe are enough. I don't know. Maybe they are enough for like some stuff, like potentially self-hosting the language, although I'd say that could be a bit difficult. But yeah, like I'm pretty sure that self-hosting the cool language would be much easier because it's more featureful, but that's also the problem, right? How the more complex a language is, the more time it takes to write a self-host compiler. So it's that's the trade-off. If you have it really simple, then it's easier in a way to write a self-hosted compiler, but it's also harder because you don't have enough instructions and features. But yeah, I mean, maybe we can find a good balance between the two. So yeah, I think, yeah, I don't know, maybe next time we can start to parse these kind of things. I'm pretty sure an AST is required if we want to have these kind of structures, right? But I'm not sure how I'm gonna represent this thing in the AST. Maybe it's just purely a list of like you can see that here we only have operations. Probably it's gonna be operations and literals. But yeah, we also need if statements. That's the most important part, right? Because if we have if statements, we basically have like if statements and functions. That kind of means that we have what is like Turing complete language, right? So we would need if. Yeah, I think if statements are enough if you have functions, because you can jump to other functions and simulate while loops. So that should be enough. You can do recursive stuff. Yeah, I think, yeah. So I just have to figure out how I want to make the if statements look. That's the next step. maybe conditionals. And yeah, let's try to build some AST for this stuff. Right, we should add the keywords, tokens, and then some kind of AST, and we'll see where this thing leads. Maybe it's gonna be funny language to use, I don't know. So yeah, hopefully it was useful to see some assembly for today. I think I remembered how to do quite a lot of things with assembly, so hopefully it was not that confusing for you. And yeah, the part from C was quite easy to get, I guess. It was just printing the assembly that we worked here to get. So yeah. All right, so I guess we'll see next time when we try to implement the proper language, the proper stack lang. So see you next time.